So I want to take the idea of multiplication rule and I want to apply it to a new situation. But also when we do this example, we're actually going to tie together a bunch of ideas we've already come across, definitions as well as basic rules, tree diagrams, and such. And we're going to use this example in the next chapter to kind of drive some ideas for section 6.2 in particular. So let's look it over. Suppose the average free throw percentage for an NBA player is 77%, which is the chances they will shoot a successful free throw. That's the one where they sit at the end of the line, like somebody's fouled them, so they get to stand at the end of the line with nobody bugging them and take a shot. That's a free throw. So you're going to randomly select three random independent NBA players and have each of them shoot a free throw. All right. So for each player, how many random outcomes are possible and what is the associated probability for each? Which, by the way, this is the NBA average. I looked it up. At least it was a couple years ago. All right, so when a player goes up to the line, they either succeed or they fail, right? They either make the basket or they miss the basket. So that would mean that there's two possible outcomes. The success would be that they make it, and the failure in this case would be that they miss it. Now, just keep in mind for a second a couple of things. One, the terms success and failure get used a lot in probability, but success is not always a positive thing. So if you're on this person's team, yay, success, they made it. But if you're on the opposing team, then them making it is actually failure for you. So it kind of depends on your perspective. I think I'm going to actually add that into that box for future. So also note success is not always positive and failure is not always negative. It always depends on perspective. The perspective of the person conducting the experiment or the perspective of the person trying to figure out these probabilities. All right, now how large is the sample space? Well, that's not too difficult to figure out because you have the multiplication rule of counting at your disposal. And you can use that multiplication rule counting to calculate this. So you think to yourself, well, the first player that goes up to the line, they have two options. The next player that goes up to the line also has two options, and so does the third player. And so 2 times 2 times 2 is 8. And that's good because it guides us as we make our tree diagram. We know that when we're all done with our tree diagram, we should have 8 different branches. So 3 different sections of arrows that gets us 8 branches total at the very end. So our sample space should be 8 long. Well, this is honestly the exact same tree diagram we already made for when families have 3 kids, because you have the first player going up to the line. I'll call him LeBron. There you go. Just making a name up out of thin air. So LeBron goes up to the line. He has 2 options, success or failure. Then I'll just make up another one off the top of my head. Steph. Steph goes up to the line and has 2 options, right? So LeBron could have succeeded and then Steph could succeed, or LeBron could succeed and Steph could fail, or LeBron could fail and Steph could succeed, and so on. Then I can go one further and throw another player in. Let's call him Kevin. All right, so Kevin goes up to the line and he could succeed, right? So it could be LeBron succeeds, Steph succeeds, Kevin succeeds. It could be LeBron succeeds, Steph succeeds, Kevin fails, and so on. And so you make your table and out of the tree diagram. Every single one of these little branches here, you can get to it along the line. So to get to this success for Kevin must have been success for LeBron, failure for Steph, success for Kevin. And then success for LeBron, failure for Steph, failure for Kevin, and so on. Right? The top 4 outcomes have LeBron succeeding. The bottom 4 outcomes have LeBron failing. The middle 2 right here have Steph failing, and so do these 2, and so on. So you'll have all 8 outcomes listed. Remember that it has to be vertically aligned, moving from left to right. That's the way tree diagrams are. So it's got to be all lined up. These S's and F's should be all in a perfect vertical line over each other. All right, now why are these outcomes not equally likely, which we've not had before. In section 5.1, when we first did tree diagrams, we were assuming equally likely. We remember we did it for kids, and we said, oh, M and F, we'll just assume equally likely. It's not true, not even for biological sex of kids, but we just pretended like it was. But here we actually know, in fact, that they're not. But that's okay. But let's explain why. They're not all equally likely because these are NBA players, right? NBA players in general have to have a free throw percentage that's higher than 50-50, right? Equally likely. Just for the record, one of the worst free throw shooters of all time was Shaquille O'Neal, and his overall percentage for his lifetime playing was about 50%. Right, his career in the NBA, I should say. Most professional players are much higher. This is the overall average for the NBA, but some of your best players, like a Steph Curry, for example, would be higher than that even. All right, so the probability of success is 0.77, not 50-50 like we were assuming in section 5.1, right? So that means that successes should be more likely than failures, which makes sense because they're professional basketball players. All right, so then let's use the multiplication rule of counting to find all of those outcomes as probability. That's a word, right? So we want to find the probability for every one of those outcomes. Okay, we can do that. Let me type them all up again real quick. Let's start with success, success, success. This one right here. Well, that would be the probability of success for one times the other times the other. According to the multiplication rule of counting, we'll take 0.77 times 0.77 times 0.77, and that'll get us a probability here. Let me type that all up. There, I highlighted that one in green for us. So SSS is 0.77 times 0.77 times 0.77, which would be 0.77 to the third power. Now I want you to notice that it never said and anywhere in there, but you just assume it because you want 3 successes. So it's that and is kind of hidden in the problem right here. So when you want 3 successes, that's and probability of S times probability of S times the probability of S, which speaks to that comment we made on the previous page that and often is sneaky and hides in places in the English language. So now let's do the probability of SSF, which is 0.13637, but let me prove it to you. So that's 0.77 times 0.77 times 0.23, and you'll notice 3 of them are actually that way. And that's because they all have 2 successes and 1 failure. Notice the and in there. So you're multiplying. So 0.77 times 0.23 times 0.77 is the same thing as 0.77 times 0.77 times 0.23. They're all the same. They're all 2 successes, 1 failure. All right, now what about 2 failures, 1 success? Let me type that up. All right, these 3 are a little concerning because you have 2 failures and 1 success. So I'm going to give them the orange color. So 0.23 times 0.23 times 0.77. And then last but not least, fail, fail, fail. Fail, fail, fail would be all 3 of them fail. So that's 0.23 to the third power, right? Because you want the first player to fail and the second player to fail and the third player to fail. And there we have it. We used the multiplication rule even though they weren't equally likely. So we used the tree diagram to help us develop our outcomes in a nice, ordered, structured way. And then we used the multiplication rule to be able to actually find the probabilities we were looking for. Now there is an easier way to do this, sort of, but we'll learn about that in section 6.2. So until that time, this is how we have to do it. Now let's find the probability that the first 2 are successful and the third player fails. Well, we already found that, right? First 2 is successful, third player fails. There's an order to that. It's implying that it's S, S, F, but we already found it, right? It's the probability of success times the probability of success times the probability of failure. They implied a particular order, and we're using that order, right? Something comes first, then something comes second, and so on, right? And it's 0.1367. All right, now let's look at the next question, because I wanted to trip you up here. For letter G, I want you to find the probability that 2 succeed and 1 fail. or one fails. Now, here's a hint. This is not the same question as above. To succeed and one fail, who's the failure? Is it the third person that's the failure? Or could it be the first person that's the failure? So up here, the third player fails implies that Kevin is the failure. You remember LeBron, Steph, Kevin. Just randomly chosen names. All right, so this one's saying, hey, any one of them is a failure. I just typed that up real quick. So this one implies that LeBron succeeds, Steph succeeds, and Kevin fails. But this one implies that there is no order, right? It could be any one of them that's the failure. All right, so that means that I want the probability that any two succeed and one of them fails. So that means it could be SSF, Kevin fails, or SFS, Steph fails, or FSS, LeBron fails. So we already know the probabilities for each of those because it's up above. So it's 0.13637 plus, because this is an OR problem. OR implies the addition rule. So I'm going to add these probabilities and I get 0.409101. Now notice this means that we need a warning. Probability wording is really important because these look so similar. I mean, one says the first two succeed and the third player fails, and one says two succeed and one fails. But that difference, just a little bit of language difference, implies very different answers. So that's something to keep a watch out for as you do these problems because the wording really matters. Also, always remember that and is sneaky. And will hide in these problems for you. All right, let's find the probability that at least one of the players succeeds. Well, this is leading us into a rule that we'll need a little bit later, but at least one success is basically everything, right? They're all at least one success, except for fail, 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 right? So if we want the probability of at least one success, we want the probability of all these different S ones. Now you could add up all those different S ones if you so desired. There'd be, it's a pain, but you could do it. But there's an easier way. You know that the sum of the probabilities has to be 1. As a matter of fact, I'll add that in right here at the very bottom. Like we know this has to make 1.000, right? We know it has to make 1. And if it does make 1, well then it's a lot easier. Instead of adding up the blue ones and the green ones and the orange ones, why don't I just take the pink one, subtract it from 1, and I'll have my final result. And so that's what I'll do. So I take the probability of at least one success. That's 1 minus the probability of no successes, which is the probability of fail, fail, fail. And that means I'm taking 1 minus the pink one, which was 0.012167, which means my final result is 0.987833. Now that problem right there, keep that one in mind because we're going to hit that rule in just a couple pages because that at least one thing, that's special and that will come back to us a lot.